So let's continue with the heap lecture, and just like last time, let's start with a question, but it's an easy one this time. So we have a collection of stones, and each stone has a positive integer weight. And in each turn, we choose two of the heaviest stones and smash them together. So if those stones were equal, then both stones are totally destroyed. But if they're not equal, then the weight of the largest stone will become the weight of the largest stone minus the weight of the smallest one. So let's take the example here. So for now, the largest stones are 7 and 8, right? So on the first turn, we take 7 and 8 and smash them together. And since they're not equal, we take 8 minus 7 and then add it back into the list because it's not completely destroyed. So in the next turn, our list becomes 1, and then this is 1, so we add 1. Right, yeah. And then in the second turn, again, we take the two largest ones, 2 and 4. We smash them together, still they're not equal, so it will be 4 minus 2. So our list becomes 1, 1, 1, 2. So then we continue like that. We take this largest 2, smash them together, and then it will be 1, 1, 1. Then again the largest, since they are equal, they are completely destroyed. So we only have 1 left, so we return 1 again. And if we have nothing left, we return 0. So how could we solve this?
You understand the problem?
Any questions about the problem?
So order is not matter, sir. I mean, doesn't matter.
You just need the two largest ones in every time.
Any questions? So you all understand the problem? Same. You understand the problem?
So how would we solve it? Any preferred solution?
We search for the maximum number, and then we search for the second maximum number, find the difference, and create a new array, and populate that array.
Okay.
And repeat it.
You can do that.
Cool.
So that's one way to do it. But it would be inefficient, right? For every turn, we have to look through the whole array to find the two maximum ones. So something we can do is we can have this, like, it's just a box for now. We have this box, let's say. And what this does is we just give it all of our numbers, all of this array, and every time we ask for it, it gives us either the smallest number or the largest number. So in this case, let's say we told it to give us the largest number. So it's already let's say it already has a whole array in here. So when we ask for it for the first time, it gives us 8. Then when we ask again, it gives us 7. So we smash them together, this becomes 1, right? So we add 1 into the box again. So when we ask again, it gives us the next larger ones are going to be 2 and 4. So it gives us 2 and 4, so this becomes 2, and then you add this 2 back here again. And then it continues like that. And every time it gives us this largest number or the smallest number, it does it in all of one time. So it will make our solution to this problem a lot more efficient. Does that make sense?
Like basically what you did, but what if there was a way to not take off in time to find the biggest number?
Makes sense, right? So this books, we call it a heap. And in this specific case, it's called a max heap because it gives us the biggest number. So let's go to the definition of a heap. So it can be two kinds. It could be a min heap or a max heap. Like min heap gives us the smallest number, max heap gives us the largest number, as we saw in the example here. And so what a heap basically is, it's a type of tree, and specifically it's a complete tree. And in this tree, each node is smaller than or equals to its children, when in the case of a min heap, and in the case of a max heap, each node is greater than its children. So as we can see here, there's an example of a max heap. So there's 100, and both of its children, 19 and 36, are smaller than it. Same for 19, 17 and 3 are smaller than it, and it continues like that. So that's just what a heap is. So we say a heap is a complete tree, right? So, and like we talked earlier on the tree lecture, we said that a tree can be represented using an array. And if it's a complete tree, it becomes even more easier. So it's very easy to represent heaps in an array. And there's an easy formula to get the parent, the left and the right node. The parent node, for example, we can get I minus 1 over 2. For example, in this example, let's say we want to get the parent of 9. And 9's index is 6, so if we want to get the parent of 9, it's I minus 1 over 2, so 6 minus 1 over 2. It's 5 over 2, which is 2. Right? With integer division, so the it's going to be 3.
I think the index is supposed to be from 0.
Oh, right, yeah. Yeah, okay. The index is supposed to be from 0.
Give another example.
Yeah. We can just take them. So if we represent this in an array, this would be 0, 1, 2, 3, 4.
It's not complete.
Oh. So the array would be 16, 14, 10, 8, 7. And if we want to get 8's parent, for example, 8's index is 3, so it would be 3 minus 1 over 2, which is 1, and its parent is at index 1. And to get the left and the right child, it's 2i plus 1, so to get the left child of 14, it would be 2 times 1 plus 1, which is 3, and 2 times 1 plus 2, which is just a simple way of finding the parent and its children.
Does that make sense? Like they can be represented in a list, so you need a way to check which one is the left child and which one is the right child. And you can do the calculation on the indexes to find the left and right and the parent again.
So these are the main operations we would do on a heap. And the first one, heapify, means given a random binary tree, we need to change it into a heap. So that's that first. Let's say we have something like this, and let's say we want to construct a main heap. So in this case, this is not a correct heap, right? Because like 20 is greater than 30, but if this is 15. Like 15 is less than 20, and that wouldn't make a main heap. So the heapify operation is we're going to change this tree into a heap. So what we do is we start from the last element. Like if we represent this in the array, this would be the last element, right? So we start from here, and then we see this one, and compare these two, and we put the minimum of these two over here if it's less than the parent. Because what we want to do is make sure that this node is less than both of its children, right? So we take a look at this, 19 and 16, and 16 is smaller than both of them, right? So we take 16, we look at 30. If 16 is less than 30, we have to put it over here. So we exchange the places. And then we can go ahead and look at these. So the minimum of these two is 15. So we take 15 and compare it to its parent. Since it's smaller, it has to go up and be the parent. This becomes 20. This becomes 14. And this is a proper main heap, right? Did that make sense? So all we did is we just start from the leaf, from the last level. We compare their children, take the minimum of them, and then compare that with the parent. If it's smaller than the parent, it means that that number should be, the smallest number should be at the top, right? So we take it to the top. And then we go to the next level and do the same thing until we've taken like the smallest numbers up and the biggest numbers would be down. So what do you think the time complexity of Heapify would be?
Maybe let's see the other ones before we get to facts of craziness.
Okay. Okay, so the next operation is get minimum. What would we need to do to get the minimum?
Where's the minimum element in the main heap? I really can't hear you talk.
Doesn't know.
Oh.
I don't hear.
Doesn't know.
Yeah, the main heap is just a root node, and I guess the time complexity is obvious over here. It's just constant time because we just take the top. And let's say
And
we
what
want
index would be the root node, by the way, on a list? Huh? Why can't I hear you guys? I swear to God, I just hear something. Huh? 0? Nice. Because we're starting the indexing from this. Okay.
and insert. Let's say we want to insert 17, for example. So what we have to do is, since we represent a heap in the form of an array, it's going to be difficult to insert a number in the middle of an array, right? So what we want to do is just put it at the end of the array. So if we assume that 17 is put at the end of the array, it means that it's at the end of the tree too, right? So the end would be here, because the array was 2, 3, 4, and then the last index 5 will come over here, so we put 17 here. But this wouldn't be right. This wouldn't be appropriate here, right? So to fix that, we look at 17. Since it doesn't have any sibling, basically, we don't need to compare it with anything. We just compare it with the parent. It's smaller than the parent, right? So we have to take it.
So once made a new element, we have to apply Heapify operation.
Yes.
Kind, not the whole Heapify. Just up heap and down.
Okay, so Heapify basically means that the whole tree is random, so we have to go through the whole tree to make sure that every element is in the right place and to put them in the right place. But when we're inserting an element, we're not necessarily doing the whole Heapify, because we just need to make sure that the new element we've inserted finds its right place. So the process of finding the right place. Here we exchanged 17 and 20, right? So we took 17 up because it was less than the parent. So this going up operation is called upheap. So downheap is when, for example, when we find a number that was greater than its parent and we put it up, like if
I think once we have max heap, then we can use down heap.
Actually, like we can find an example for
yeah,
it.
that's
Yeah,
right.
or
Wait.
not heap, but down heap.
Maybe we can see it in the illustrations later on. But basically what upheap means is when we find a number that's greater than its, that's less than its parent, we have to pick it up, so that's called upheap. But when we find a number, when we're looking over here and we see that a number is, when we see that it's greater than its children and we take it down, that's called a downheap. And we'll look at it in properly later in the illustrations. So the insert operation makes sense, right? And then when we remove, let's see, when we remove, we always remove the root node, right? So let's say we removed 15. So what we do every time we remove from the heap is, after we remove this, we take the last elements and we put it at the top. And then we do the heap file operations to turn this tree back into a heap again. So when we take here 19 and 13, the minimum is 90, right? So 19 is greater than 60, so we don't need to do anything. When we see 16 and 17, the minimum is 16. 16 is less than 20, so we have to exchange the places. So 20 times here, and 16 times here.
You need down heap here.
Yeah, so this is a good example for down heap, because once we brought 20 down, we need to make sure that this is its exact position. So we need to check again, we need to compare this to its children. So we take the minimum of its children, 19. 19 is less than 20, so we need to bring 20 down. So this is 19. This becomes 20. So when we removed 15, we had to bring 20 from its position downward, so that's called a down heap. Does that make sense? Is it clear, like, what upheap and downheap mean?
What's the difference between down heap and up so far?
I think we have a question.
Oh, there's a question, sorry.
I don't understand heap. Do we start from the child and move up?
Yeah. So we do upkeep when we're starting from the children. We compare them with the parent and take the children upwards to bring them to their position.
How do we access the parent if we're at the child?
Good one.
Like with since it's an array, we saw how we can access the parents, how we can find the parent's index. We can also find the left and right child, so use an array. Does that make sense? So when we modify, so every time we modify, we just need to make sure that the element that we modify is also in its correct position. So here we change this to 18, but 18 is less than 19, right? So we have to take it out. This becomes 19 and this is 18. Yeah, those are all of the operations. And should we go through the time complexities now? What do you think the time complexity of N13 would be?
Third.
What is the time complexity of the insert operation?
So we're going to go isn't it
Yes.
the insert operation will be that gives off the
Yeah, it would be log of n.
One follow-up question. Is there a chance where the depth of the tree would be worse than log of n, by the way, in this case? We discussed earlier that the depth could be n, right, if it's only to the right, but in a heap, can it be more than log of n?
given requirement for a heap it should be complete.
Yes. If it's a complete tree, then it's the leaves are going to be at least one more deeper than any other node, I guess. Any other leaf.
Does it make sense why it's log of n, the time complexity? Does it? Okay, so when we inserted, what did we do? Like, we put it at the end, and then we took that element upwards one level at a time, right? You didn't have to go through the whole heap to find the position for that element. So every time the operations we do is based on the levels. So it's going to be O of the levels, and the levels are going to be log n. So it's going to be O of log n.
And each operation is just swapping, so it's going to be a constant time operation.
What about the modifier operation? It's basically the same, right? Because once we modify the element, we just need to take it to the proper position, so it's log of n.
Maybe don't.
Yeah. So, what about heapify? What do you think the time complexity is? Do you want to answer? Okay.
It's a good
What
one.
would you?
Continue, sorry. Just say it to me.
For every element, we check if, like, we do the insert, we don't do the insert, but we check if that element
We move it up. So
we do that for each element, so.
Okay. But it's O of n, right? Because for every element, every time we move it, we're also making sure that the other elements are finding their places too. So for every element, we're not exactly doing log n operations. So it's going to be O of n. Right? I don't know if that's confusing. Does that make sense?
the proof is a little more complicated. I have no idea how it's proved, but it's okay.
So ON for modifying.
No, modifying is log n.
Okay, you said for removing. What was the
Heapify.
Heapify? Okay.
Yeah.
So ON for
So we can look at the visuals here. We can start from build heap.
use once or inside one.
Look at what it's trying to do. Starting from the end and swapping them.
It's finding the minimum and swapping it with the parents if it's less than the parent. So far it's just been doing up heap because it's taking the, but now it did a down heap because after it changed it, it has to make sure that that also corresponds with the child element. I guess this makes sense, right? For inserting elements, let's try 50 per example. Let's try 30. So it added it at the end, but it compared it to the parent and put it up because it's smaller. Let's try like 20. Again, it just adds it at the end, compares it with its parents, and takes it up. That makes sense, right? Yeah, remove smallest just takes the top one and then again makes sure that it's appropriate, so it does. Do you have any questions or anything you'd like to see?
Any examples you want to run?
So the heap implementations are here. Try to implement it yourself, but then you can go through the code. And so heap applications, heap sort is one sorting algorithm that uses heap. Does anybody want to guess how that works?
Yeah, how would you sort a list using a heap? Group. And write about your name. Assume a heap is something that gives you the minimum number in an efficient way. Like, assuming we're using a max heap. I mean heap. Took some minutes. Okay.
We're going to change the array to a main heap, get the main heap, convert the array again into a main heap, and get the main heap, and we're going to do this n times. So getting a main heap is log n, I think. So doing this n times, I think n log n is first time. We just keep converting it into a main heap, get the main heap.
Yeah. We just insert all of the elements in the heap, and every time we remove one, it's rearranged and make sure that the minimum is like at the top again. So we just need to keep on removing. A priority queue. An emergency room is one example of the problem. So priority queue basically means a mean heap. It gives you the smallest number, and I guess in emergency rooms you can give like priority to based on the people's injuries or something, so it can be used to prioritize the it's also used in some graph algorithms, like the shortest path, for example. I think we'll be seeing it in other lectures. So solution to the first problem. Basically, all we need to do is just create a max heap and take the maximum out every time. Over here in Python, if you notice, every time we put it into the heap, we make the weight into negative. That's because in Python, heap basically in most languages is already implemented. You're usually not going to be asked to implement it yourself. You're just going to use the already existing library. And in Python, I think only a mean heap exists, so to change it into a max heap, you can turn the numbers into negative, because that means like the biggest number would become the smallest number when it's negative. So you can just change them to negative and put it in. But in other languages, like Java, for example, you can just create your own comparator for the min heap, and it would just become a max heap, and then you can just continue. And then try the first problem, and you could look at the code. So some tips. Heap is a tool. Like I said, it's mostly implemented in all languages, so you're probably not going to be asked to implement it in interviews. You just use it as a tool to solve the problems. And yeah, you won't have to implement a heap. And I mean, heap can work as a max heap by turning the values into negative. And yeah, that's it for heaps, if you want to add anything.
Heap cute, I guess.
Yeah. Then there's the exercises. And the last quote of the day is, "It's the possibility of having a dream come true that makes life interesting." It's from The Alchemist by Paulo Coelho. Thank you, everyone.